So here we are with part 4 for kinetics. And this is going to be a review, partly, of what we did in class the other day, looking at the graphs that will be linear. So for a zero order process, concentration versus time is linear. Okay? We saw this in class the other day. Concentration of A versus time, linear plot. Okay? Linear because the rate does not change as the concentration of A changes. Here is an example of a zero order linear plot of concentration versus time in hours. Now, what if I ask you now to sketch a different graph, which is rate of this zero order process per time? If you think back, the rate is constant, therefore in this case I would get a horizontal line. Mine's a little wobbly. Okay, since I have a constant rate, this is what the graph of rate versus time would look like. And this we did not talk about in class. Here we have a first order process. Okay, concentration versus time is not linear. However, natural log of concentration versus time is linear. And in this case, the slope of this line would be the negative of the rate law constant. Here we have a second order process. In order to get a linear graph for second order, we need to plot 1 over the concentration of A versus time. This one has a positive slope. The other two had a negative slope. This one is positive. Here is a summary of something we did in class the other day. You may already have this written down. You might want to check, though, to make sure that you transcribed it correctly in class. I suggested that you do that by checking in the book. But here you go. Here's the same information with the additional information about the slope and what the slope actually represents. So do make sure you have this someplace in your notes where you can get to it quickly if needed. So here's another chance to look at graphs of concentration versus, rate versus concentration. All right. Zero order, the rate does not change as concentration changes. First order, the rate is directly proportional to the concentration. So if you double the concentration, the rate goes up by a factor of 2. Second order, it is exponential increase because if you double the concentration of A, the rate goes up by a factor of 4. Okay? So these are a variety of other graphs. All right? I can't promise you that you're necessarily always going to have a graph that is similar to the ones you have seen, which is why in this presentation I'm showing you a variety of other graphs, okay, so that you maybe diversify your portfolio a little bit. So take the time, if needed, to go back, rewind, and look at these again. I don't know that you need to put them all in your notebook, but that's totally up to you. Now I'd like to talk a little bit about reaction mechanisms. If you think about the word mechanism, I generally think of a mechanism as sort of a way that something works. Okay? And when we talk about reaction mechanisms, we're talking about how a complex process happens by breaking it down into a series of individual steps. Elementary steps are reactions that take place in a single step by a single collision between particles. Okay? So if I were to tell you, and they always will, that these processes happen by an elementary step, it means that two particles of A bump into each other and form the products by a single collision. In that case, we can actually write the rate law simply based on the stoichiometry of the reactants. So since there are two A's, the A is squared in the rate law. In this case, I have A and B. They each show up in the rate law once. Here I have these three that each show up in the rate law once. And here I have 5 different particles, and they show up as you see in the rate law. Okay? Now, writing then this rate law is pretty easy to do, but let's talk about how likely is a single collision going to be. Okay? It's probably not terribly unlikely that 2 particles can hit each other in just the right way with the right activation energy. But as we increase the particles to 3, or in this case even 5, the odds are very much against a single collision happening in a successful manner. Okay? The number of particles in these elementary steps are sometimes called molecularity. So you could see that the first one has a molecularity of 2. The last one has a molecularity of 5. Okay? And a collision of 5 particles is extremely unlikely. What this means is for a process that includes 3, 4, or more particles having to collide, and actually sometimes even 2 particles needing to collide, depending on what those particles are, the odds may not be very much in favor of that happening in a single step. So I'm going to tell you a little story here that I think illustrates what I'm talking about. Cleaning up holiday dinner with my family, okay, is really not a single step process. Okay, I see this as a variety of steps. And let me jot down what some of those steps are. So if you humor me for a moment here, I can envision this process of cleaning up as a number of things, starting with clearing the table, wrapping the leftovers, rinsing the dishes, loading the dishwasher, scrubbing the pots and pans, and drying and putting everything away. Now, if you think about this, these steps have to happen in a sequence, all right? And not all the steps are going to be equally lengthy. Some of them will be quick, and some of them will be slow. For the sake of this example, I'm going to label the steps as you see, and I'm going to say that if you were to do all of these steps, I would envision the scrubbing out the grubby pots and pans is probably the slow step, okay? And this step would then be called the rate determining step of my mechanism, okay? It is the rate determining step that holds up the entire process and ultimately determines the overall rate, okay? Rate determining step. That's how I abbreviate it. So if we talk about this for a moment, consider the following. The rate determining step is the one that holds up the entire process. So adding reinforcements, adding more reactants, adding more people to help with the rate determining step will probably help the overall reaction get done faster. However, adding more people to clear the table won't really help the overall process go faster. Adding more people to rinse the dishes isn't going to help, okay? And so adding more reactants in a rate determining step does speed up a reaction, but adding reactants to an already fast step does not help the reaction get faster. And that's how we can have a zero order reactant. If the zero order reactant participates in a fast step, adding more of it and increasing its concentration will not make the overall reaction faster. Let's let these two equations represent a series of two steps that happen, okay? What is the overall reaction that happens at the completion of both of these steps? I think you'll notice that the AB that formed in step 1 is consumed in step 2 and can be called an intermediate. It's something that forms but does not remain. It's an intermediate in the process. The overall reaction here then would be A plus B plus Q makes Z. Okay? Now, I will also tell you that the slow step determines the rate law. So, if step 1 is the slow step, the rate law will read as follows. Because there is 1A and 1B in the first step, if that step is slow, the rate law depends on the stoichiometry of that step. However, if the second step is slow, okay, the only reactant present in the second step is Q, and so Q is the reactant that shows up in the rate law. Here's one more example, given a series of 3 steps. What would the rate law be with the given information provided? Step 1 is slow. Therefore, this would be your rate law, based only upon the slow step. Now, one last thing before we end. What is the overall reaction for this process? So pause the video, see if you can identify any intermediates, things that form and then are consumed, and then cancel those out and see if you can write the overall equation. I notice that an intermediate seems to be forming in the first step and being used in the second. I also notice another intermediate forming in the second step and being used in the third. And that results in the following overall process. Okay, that just about does it for part 4. I will fill in the little gaps when we're in class together. Good job. Thanks for listening.